All right, and I'm recording. We're start. Hey, Rutherford scattering. We're done with chapter 3 in the textbook. We're moving on to chapter 4. Rutherford scattering is the first clue as to what is going on inside an atom. And there's some great words in the book and in my pre-lecture video about what people thought an atom looked like. Um, moving at the turn of the century, the 1900s, and even back to the Greeks, where they knew there was something, earth, air, fire, water, and these things combined somehow and gave us the other elements that were known. Pretty soon, it became clear that that just wasn't the case, and so. Guy named Thomson, J.J. Thomson, who you remember he was the one who turned the cathode rays into electron beams because he gets credit with discovering electrons. He had a model for an atom, and that's discussed a little bit. His thought was, I think, modeled after what a biological cell looked like. He thought positive charge was somehow smeared out over some range, and then electrons, which he invented or he discovered or whatever we give to the name of what he did for cathode rays to turn them into electrons. He thought that his electrons were sort of just stuck in this, I don't know, gelatinous goo of positive charge, and that was the model for a while. And Rutherford's experiment, what we're talking about today, is what disproves that. Any questions about anything you saw? I apologize for the video because it's long. The derivation of the Rutherford equations boil down to three equations at the end that I'll highlight here in a second after I show you an animation. I hate the derivation because it's nothing clean like Newton's second law or any of the mathematical laws that govern electricity and magnetism. I can't start with that. It's more like chemistry, where you're doing dimensional analysis and making things work out, looking at areas and counting things. So in terms of going through the book or going through my notes, uh, it's hard to follow. I will say this: after I did the video, I've also posted. I just did it this morning. A 2-page handout that works through the math that we talked about. It's an alternative to the book. One of the things you always notice about textbooks is they give the big steps and they leave out a lot of the mathematical detail in between. And that's what my handout hopefully does. And I tried to do that in the video last night. The result was a 45-minute long video that I'm not sure was inspiring. Certainly not something ready for National Geographic Channel or anything like that. Any event, I do want to show you because the math is great and you're going to have to do calculations, but I want to show you an animation of Rutherford scattering and just make some comments. I think this University of Edmonton and their visualization center, they did a really good job with this one. So unless there's any questions before we get started, I'll move right over to that. And why do I have to? Oh, that's the desktop. All right, and hopefully you're seeing this is from their site. And I'm going to start off with Rutherford's prediction. And hopefully you're seeing a gold atom sitting right there in the middle. And this is meant to be an electron right here. I kind of like the auto fire mode because you get the picture of what's going on. There's one going right through the center. And notice that one started off a little bit offset. That one's not as much offset. And as I'm talking, you can see that this parameter right here, and let me grab a annotate tool. Hopefully I can draw with this. We call this parameter right here, and I'll just go to the most extreme one, the impact parameter. Anybody that's played billiards or shuffleboard in a bar or something like that knows if you don't hit head on, you can cause glancing collisions. And that's sort of what Rutherford was expecting here. And he expected a very slight angle based on these glancing collisions, no great angles. And this would be consistent with J.J. Thomson's plum pudding model with electrons stuck in this gelatinous goo of positive charge, like raisins in plum pudding. That's the analogy. And he wasn't expecting big angles of deflection as the item that's coming in. And by the way, that's generally alpha particles. Those are alphas, and that means 2 protons and 2 neutrons. I don't know how to make a neutron, X's. Okay, that's what an alpha particle is. It's a helium atom without the electrons. And that's what he expected. Of course, the rest of the story is that is not what he got. Okay, when he did this, I can probably kill that one. What he saw, and I guess we'll show you the experiment first. of what he did. Let me clear my chicken scratches there. Um, Apparatus like, nope, come on, give me my cursor back. Apparatus like this is key, and so you put the detector here at some angle, and now I want my annotate tool back. I want to be able to draw on this. You have alpha particles or something come shooting this way, hits a very thin foil, right? And then we're looking at these deflection angles. And what I just showed you on the simulation is Rutherford expected there to be very small deflections, 5 degrees maybe even or less. And I'll start firing particles here if I get my cursor back. And all of a sudden at 15 degrees, you're still seeing a lot of particles. Let's stop that. Move it out to 25 degrees. We're still seeing a lot of particles. And this, by the way, is alpha particles. I selected the gold element for my foil right down here in the bottom, fire a bunch more particles. Greater angles, less, but you saw all the angles in his prediction were less than about 5 degrees. And even at 45 degrees, I'm still getting quite a few particles. Let's see if I can get any to backscatter. Yeah, we probably have to wait too long, but he even did see some that would backscatter. And that's what I mean when the angle here is greater than 90 degrees. And I guess you can do the same thing on the other side. All right. And this is a fairly classic experiment for scattering. If you think about it, scattering is one of the most important kind of techniques in physics today. All the nuclear physicists who have accelerators, even as big as CERN or just some of the ones Brookhaven on Long Island or Fermilab outside Chicago, they get particles moving real fast, like this box right here for the alpha particles, and then they collide it with something else. In Rutherford's case, it was a gold foil or a silver foil or an aluminum foil or whatever he used, and measured what came out. The big accelerators have not just one detector they can swing around here, but just an array of detectors all around the experiment after the scattering is done. And you back calculate and try to glean information from what you see from the scattering experiment. Probably one of the most important ideas in physics. And that's why I think the Rutherford derivation, even though I hate doing it, and you probably hated looking at it for 45 minutes, it's important that you see the kind of things that go into a scattering experiment's predictions. All right. So anyway, everybody good on what the experiment looks like? Okay, so now we'll look at some of the results that Rutherford got. And I'll clear my chicken scratches here again. And we'll look at the nuclear atom. And let's see, there's an impact parameter is 0 right now. There's that impact parameter symbol was B, right? And let's auto fire a couple times. And still not seeing. Oh, there's one that comes back. You can see if it just perfectly hits the nucleus, it comes right back. But I don't know that all the forces are properly being considered here. I'm not crazy about this particular animation, so I'm going to kill it. Let's go on to the next one, the scattering explanation, which I think does a reasonable job of the same thing. There's my alpha particle again. There's my gold nucleus. In this case, I can change it to platinum, aluminum, lead, whatever. Let's auto fire and watch a bunch. Okay, that one came straight in. Wow, now look what happens. Okay, and so you get electrostatic repulsion. You don't even have to have a collision. Okay, and I like watching this build up over time, and you can see all the possible impact parameters are just kind of randomly selected, big ones like that one, small ones like that one, and you can get fairly large deviation in the scattering. And this is what Rutherford and his colleagues saw. That's Geiger and Marsden were his colleagues. This is the kind of thing they saw. You can see there's this region because this is a positive gold nucleus and this is a positive alpha particle. You never get close enough at this particular speed. Now, I suppose, let's clear this because I think it's interesting. Impact parameter you notice is varying randomly by the simulation. Let me give the alpha particle more energy. So we'll stop here. Okay. I'll clear it and I'll give the alpha particle greater energy. And let's watch what happens. And it's the same sort of thing, but now the alpha particles, because they have initially more kinetic energy, they're able to get closer to the nucleus, right? And so the same pattern, it's just the separation between the alpha particle and the incident. I'm sorry, between the aluminum atom and the incident alpha particle, that gets a little closer here, but you still see the same sort of effect. Okay, there are areas where the alpha particle just doesn't have enough energy to go. One of the experiments that Rutherford and his folks did is that one right there, where you saw it came right in on the axis and turns around. And he was able to estimate when exactly he gave it too much energy, when the incident alpha particle, too much energy, and then it overcame the electrostatic repulsion, actually maybe collided with the aluminum or gold or platinum or lead or whatever the target atom was. And then he realized, well, he shot the alpha particle so fast that it just wasn't repelling and coming straight back. And from that, he's able to do a calculation estimating what the size of the nucleus of the atom was. And one of the groups, when we're done looking at the simulation, is going to do that calculation. And that was the first experimental measurement of what the size of a nucleus is. And before that, we'd known that the size of the atom was about 10 to the minus 10th meters. And now we're getting a first estimate of what the size of the nucleus is inside of an atom. I enjoy watching this, but we got to stop, move on to the next thing. Um, I guess scattering and structure. Yeah, it's going to be the same thing. Let's go on to the last one. Yeah, and I just want to, from that experiment I just spoke of, look at what the scale of an atom is then. And these clouds that you're seeing right now are atoms, right? And that's all the electrons around it. And we'll talk about how they're distributed. Don't think planetary model, although I'm sure there were early scientists who thought exactly that. But now, to scale, let's try to look in at one of the atoms, and I think I can move in with my arrow key here. It's going to let me move. Let's see. Yeah, there it is. Okay, so I'm zooming in on one of the atoms, and right about now, you may start to be noticing these dots right in here. Okay, and those dots are the nucleus drawn to scale. And we can kind of zoom in on one of the atoms. If I can put it at the center of the screen, wrong way. And that's probably pretty good. You can see now I'm kind of coming in along a line of nucleuses right there. And you can see relatively what the scale would be. Okay, so the size of the atom where the electrons are versus the size that Rutherford calculates for the nucleus. Okay, that's the simulation. That's the kind of big picture result of what we think an atom looks like. I think this thing will even let you go inside, right? Oh yeah, and I can make the just show the nucleuses if you're not seeing them. See those dots that are on here, and then let's put the rest of the atom back. Reset. Just resets me all the way back. Okay, and you can see how, according to Rutherford and his experiments, how small the nucleus is relative to the atom. So I'm going to stop sharing that. And I'm going to go over to my PowerPoint real quick. And bottom line, I guess, what are the three equations you need to take away and be able to do problems with? And there are three problems here today that I think are very representative of what you should be able to do. And so let me share this with you. All right, where is the share command? There it is. And yep, you should be seeing it. I'm going to go to slideshow mode because I notice sometimes in this particular mode, the division signs, the horizontal lines kind of get washed out, whereas they are present here. And the first equation that you have to come to grips with, I guess, is, I need an annotate tool here, so let me get a pen, is this guy right here. And the significance of that is it relates the impact parameter, why it's subscripted with a 0 there, I don't know, that impact parameter, to what the ultimate angle of scattering is. And even if you didn't follow the derivation of how I got this, it was kind of a mathy thing dealing with adding momentum, actually subtracting momentums to finding a change in momentum, and then using impulse momentum ideas and the force that's causing the impulse being the electrostatic force, Coulomb's law. You put that all together and you turn a crank, and son of a gun, you find a mathematical relationship between B and that angle theta. And how often is it a cotangent? I mean, how many physical laws come out as a cotangent, which is one of the reasons why I also don't like the Rutherford experiment and his derivations. It's just not something people are familiar with. Can anybody draw, for example, a cotangent curve? I usually have to go look it up to remind myself what a cotangent looks like. But that is the relationship. And so if we tell you B and we tell you um, what the kinetic energy is, that's what the capital K is. What the atomic numbers of the incident thing, that's Z1. So for an alpha particle, it's helium. Its atomic number is 2. You go to a periodic table, look that up. If it's gold, I think gold's just because I've used it recently. I think the atomic number of gold is 79. That would be Z2. And then I just hate, where did that come from? I've lost my cursor. This is what happens here. There's the 1/8 pi epsilon 0 factor, though. Remember that Coulomb's constant K is 1/4 pi epsilon 0. So I guess that's Coulomb's constant divided by 2. And then, of course, it's multiplied by E squared. I'm going to jump out of this. Hopefully, it'll get me my cursor back. Yeah, that's why I hate Zoom for this one thing, and that's why I always hate going to this particular mode. All right, well, I got the one equation out while I'm here before, because I'm probably going to have to shut down PowerPoint completely. The next equation is that one that I've labeled N scattered from the cross section that is defined by the area of that impact parameter. Okay, that's referred to as the fraction of incident particles scattered. And you can see that fraction is proportional to the impact parameter squared. So the fraction is proportional to cotangent squared of theta over 2, of course, is in there. I didn't say it, but yeah, of course, have to remember to divide by 2. And that was just part of the geometry of the derivation. So that's the second equation that you have to come to grips with. And the one thing to remember on that is that N is a number per volume, usually a number per centimeter cubed for chemists, a number per meter cubed for physicists. And that's calculated by taking a density, an Avogadro's number, and dividing it by a gram molecular weight. It's a very stoichiometric sort of calculation. If a particular target is a molecule instead of an atom, that N sub m is the number of atoms that's in a molecule. Okay, so gold is 1, but if you had a diatomic or some other molecule as your target, you would have to multiply by 2 or 3 or however many atoms were in the molecule. And then that T is, of course, just the thickness of the foil. And that's what those are. All right, now I'm going to try to stop sharing or get out of why I've lost my cursor. Usually I can find it if I put it up near the top. Otherwise, I'm completely locked out. It's not letting me do that. There it is. Okay, so I can see it up at the top there. Come on down. I literally get the shadow of the cursor, which sometimes lets me recover. Yes, got it back. All right. Yeah, the issue always comes about in Zoom when I try to annotate in this mode of PowerPoint, but I got my cursor back now. Got lucky. All right, here's the next equation, though, that you have to come to grips with, and it's the third one. And I'll get rid of my chicken screw. Oh, I don't want to go back there, though. Yeah, clear it. Clear all my drawings. This last equation down here for the number of counts that you get at a particular angle And the odd thing about this is it's inversely proportional to the kinetic energy squared is what we showed. And it's inversely proportional to the sine of theta, theta over 2, to the fourth power. Okay, sort of a bizarre result. The only other thing I want to mention is this thing in the bracket. Oh, look, I got a cursor to draw with now. All right, that guy right there, if you notice, that is Ke squared, right? Coulomb's constant times the charge on an electron squared. And of course, it's also squared. And there's that NT term I was just talking about before. Ni is the number of things that are coming in over here. Okay. And the Z's are the atomic numbers of the incident particle and the scatterer, the gold, the platinum, whatever. And K, I said, is Coulomb's, is kinetic energy. And then R is just a distance you are away at any time. So R would be that distance right there. Okay. I do want to talk about this constant here because, again, in modern physics, let me escape out of here. Maybe not. Let's close that while I still have a cursor. Stop sharing, and that should close out of there. Stop sharing, and then close this. And I want to go over to a PDF document real quick, the equation sheet that we have for the course. And I just want to show you why that's a useful grouping. Maybe I'll show you that if it's open. It's open right there. Let's close that up. Nothing's working anymore in Zoom. Close that guy. And let's try to share it. I found it that time. Sometimes if a window is farther back. Now, hopefully you're seeing our equation sheet for the course. It's got all the material that's on the front and back cover of your book. Okay, go to this useful combination of constants and look right here at that line, and you see you've got exactly K, Coulomb's constant, 1 over 4 pi epsilon 0 times E squared. And it drives me nuts that people want to write 3 letters when they can replace that with a K in the denominator. But regardless, you can write it however you feel is most appropriate. I like the shorter version. Your textbook will always write 1 over 4 pi epsilon 0. But regardless, you've got those combinations of constants written out in either joule meters or EV meters, depending on which unit you need. So when you're doing the calculation, you decide, do you want to go 1.6 times 10 to the minus 19th coulombs squared, multiply it by Coulomb's constant, 9 times 10 to the ninth Newton meter squared per Coulomb squared. Do you want to do that, or do you want to just come to this table and pull off the constant? It's your call. And if you want to put in 1 over 4 pi and 8.85 times 10 to the minus 12th Coulomb squared per Newton meter squared, which is the permittivity of free space, and multiply all 4 of those numbers, again, your call. The equation sheet for constant grouping of modern physics constants is often very handy because it causes you to make fewer mistakes, literally as you're just entering numbers in your calculator doing problems. Okay, and so I'll stop sharing that. Any questions about anything that I've said? All right, well then let's talk about the worksheet. Do I have it open? And we'll break up into groups here if everybody's happy. Maybe I didn't open the worksheet, so let's open it up. And there it is. And hopefully I should be able to share that back with you. And don't do that. And we'll share that. And we got 2 problems. One group is going to look at the collision that was a head-on collision, which allowed Rutherford to do an estimate of how close the target gold and the incident alpha particle were getting to each other, which was his first estimate of what the size of the nucleus was. So one group's going to do that. And your answer, if you were paying attention the other day and you remember, we think the nucleus of an atom is about 10 to the minus 15th meters. Okay. And so that's the size you should be getting roughly for this group. The next group is going to be looking at an angle of 20 degrees and figuring out what the impact parameter B must be for that scattering angle. And then the last group is going to try to estimate based on that 1 over sine to the fourth power of the angle over 2 relationship between two known places, a 6 degree 2000 counts, and then how many counts you're going to get at 50 degrees. And my advice for this is kind of think about ratios, like on the ACT or the SAT test. It was A is to B is C is to D. Use that idea. You don't have to go through and calculate all the constants. You could, from the fact that you know that there's 2000 counts at 6 degrees, but only use the important parts of the equation to figure out what the number of counts will be at 50 degrees. And then at the end of the day, you're comparing that to the sensitivity. Is it the sensitivity of this counter is 1 count every second? And the bottom line is, when you get the number of counts you're getting at 50 degrees, is it greater than or less than 1 count every second? And these are 3 different problems. You only have to do one, your groups. And so the presenting them at the end is kind of an important aspect, because on the homework, which is due, I guess I made it due Thursday this week in WebAssign, you're pretty much going to see one of each of these type of problems. And even though you're only going to practice one today, it's kind of important that everybody briefs each other so that everybody can do all the problems, all 3 types on the homework. Questions on any of that? Then I'm going to go to breakout groups here, and we'll go 3 rooms. And in room 1, Prince, Sam, Saeed. Room 2, Amaya, Justin, Shneha. Room 3, Anaya, and Max. Any questions? Off you go. I'll visit each room.
So at least we know if we're right or wrong. We're close. It's a good part about this one.
All right. What's the big number you're going to use?
Big number.
Yeah, it's the, how do you start with that 7.7 MeV? What do you figure they're telling you there?
Um, or alpha particle had an energy greater than 7 point. So, um, that's our kinetic energy.
Yeah, and that's how I would interpret it as well. That, I always hate problem statements like this. I literally copied this problem from someplace, I forget where. I really would prefer that in my exams, I'll try to really should say that is the kinetic energy. Okay, and so then just set it equal to the potential energy when the particle stops, right? And that's what that equation is doing for you. Solve for R.
And we have our V equals 2, V equals 13.
Yep.
Okay.
Yeah, and my advice is, if you notice, you've got KE squared there kind of hidden, 1 over 4 pi epsilon 0 E squared. So that constant, as opposed to putting in E 1.6 times 10 to minus 19, putting in Coulomb's constant, my advice is to go to that table. If you need me to pull it up, I can for you. You may decide, yeah, okay, you got it right there. Use that constant. And that, I think that'll make your calculation go a little quicker. You just won't have to enter as many numbers in your calculator. All right.
Yeah.
You guys good to go then?
Yeah, I think so.
You bet. I'll leave you alone then. Okay. So I don't want to do that to you. I'll let you keep going and I'll leave. Now, if I had shared, it would have overrode you. So I didn't want to do that. We'll see you in a bit.